Okay, right, let's have a look at this. Kenneth and Ken are moving a mass 50 kilograms on a rough horizontal force, so the direction must be that way. Oops, sorry. Direction is that way. So Clive's pushing, Ken's pulling in the same direction. It said it's rough, so the resistance must be that way. Okay, initially the box is in equilibrium with Clive pushing with a force of 60 newtons and Ken not pulling at all. What's the resistance? Well, if it's in equilibrium and it's not moving anywhere, it must be the same, equal and opposite to Clive's push. So the resistance must be 60 newtons. Okay. Right, part 2. Ken now adds a pull of 70 newtons to Clive's push of 60 and it still remains in equilibrium. So if we put on here, Ken's pulling 70 newtons, but in that direction it must be 70 cos 30 in that direction. So it's still in equilibrium. What's the motion now? So now R is going to be, if it equal to 60 plus 70 cos 30, and you should get to 3 significant figures, 121 newtons. Okay, part 3. Calculate the normal reaction of the floor on the box. Okay, so what have I got? I've got my box, I've got my normal reaction to 50G that way, I've got 60 newtons going that way, I've got 70 sine 30 going that way, and I've got 70 cos 30 going that way. So resolving vertically, okay, I've got R plus 70 sine 30 equals 50G. Whoop, I put 5G, don't know why. Equals 50G. So R equals 50G minus 70 sine 30, and you should get, I don't know how to do that, R equals 455 newtons. Let's just put that there, tidy that up. Okay, so we've done the resistance, we've done the normal reaction. Now, Clive now pushes with a force of 160 newtons, but Ken doesn't pull at all. Okay, calculate the acceleration of the box. So what have I got? Let's have a look. I've got, in pushing with 160 newtons, there's no pulling. I've got 50 kilogram. Okay, what's the acceleration? So, using Newton's second law, I have got, now let's have a look. We need to think about the resistance. So, if you go back to part 1, resistance of the box, let's have a look. We've got F equals MA. My resistance this way is going to be 125 newtons. So 160 minus 125 equals 50A. So 35 equals 50A. So 35 over 50 equals A, which is equal to 0.7 metres per second squared. Okay, so we've done that. Clive stops pushing when the box has a speed of 1.5, so V equals 1.5. How far does the box then slide before coming to rest? So it's not, doesn't have any force on it, only the resistance. So we know the resistance is 125 newtons. Okay, so we've got minus 125 equals mass times acceleration. So the acceleration is going to be minus 2.5 metres per second squared. We know that he stopped when the speed was 1.5. So v squared equals u squared plus 2as. How long is it going to stop? So it's going to be, how long before it stops? So the velocity at the end will be 0, 1.5 squared, plus 2 times minus 2.5 times s. So rearranging it, you've got 5s equals 1.5 squared. That is right, isn't it? Yeah. So s equals 1.5 squared over 5, and you'll get 0.45 metres. Right, so that's part 4 done. I'll just put that there in case you lose it. Right, they now try again. Ken pulls with a force of Q newtons. Clive pushes with a force of 160. The frictional resistance to sliding of the box is now 115 newtons, and the acceleration is 3 metres per second squared. Calculate the value of Q. Right, change my colour. So what have they said? Right, they've said Ken is pushing with 160 newtons. Clive, we don't know, it is Q newtons, and presumably it's still at 30 degrees, so this is Q cos 30. And they've said that the frictional resistance is now 115 newtons, and the acceleration is 3 metres per second squared. Okay, so using Newton's second law of motion, F equals ma. What have I got? I've got 160 plus Q cos 30 minus 115, whoops, equals mass, sorry, put that in, which is 50 times 3. So rearranging Q cos 30 equals, I think when you sort all that out, it equals 105. So Q is 105 over cos 30. And you should get 121 newtons to 3 significance figures. Okay. Right.